Hi everyone, I'm Rishi, and today we're going to be discussing observables on quantum bits. Before we jump in, I want to define what a linear operator is. A linear operator is a map on a vector space that preserves the linear structure. It has to follow the following properties. A property of addition, where you have two states like so, and you distribute the operator onto those two states. It also has to have this property of multiplication, like so. So the reason why I'm defining a linear operator is because quantum observables is always represented by linear operators. But what is an observable? In classical physics, observables are any physical property of a system that can be directly measured and observed. So let's take the temperature of a room, for example. That can be measured in degrees of Celsius or Fahrenheit. Or let's take the speed of a car. That can be measured in terms of meters per second. In this video, we're going to use observables of systems of particles. So this includes position, which can be observed in meters, velocity, meters per second, energy, joules, and momentum, which is uh, kilograms times meters per second, and also angular momentum. Now, let's take that classical and turn it into quantum systems. So let's say we have a particle here, and we have a device that can measure angular momentum. So let's say our device measured angular momentum of 0.7 newtons times meters times seconds. Then our quantum state has to include that value. So we have a quantum state psi, which includes that value. Let's say instead it measures a value of 1.7. Then we have to have a different quantum state that includes that value. I hope you could see how we can have a list of possible values and a corresponding state. So we have one and two, and we have a corresponding state for those. I don't know about you, but to me, this screams eigenvalues and eigenvectors. If you want to learn more about eigenvalues and eigenvectors, I suggest you watch our first video about linear algebra. So these eigenvectors can also be called eigenstates, where an eigenstate is just eigenvectors of a linear operator. So now we have a list of possible values and the corresponding eigenstates. We can rewrite our initial quantum state to be a linear combination of all the possible eigenvalue and eigenvectors. Like so. The eigenstates in this case are going to be all the outcomes possible of this particle. And also a reminder, I write in vector state here, but this is actually referring to the quantum state psi. This was discussed in our lecture video too, just as a reminder. But this is, of course, so now we just rewrote our quantum state in terms of an angular momentum. But let's say we want to rewrite it in terms of energy. You could do so by doing the linear combination of all the eigenvalues and eigenvectors, like so. That's energy. But you can also do that for position. Position's a little different because it will be a continuous function. So it'll be written something like this. All we're doing here is the same quantum state. We're writing it in different bases. This is similar to changing the coordinate system in a classical problem. So let's recap over here. If we have an observable A, it can be written as a matrix in the complex set. So like this. Another property of A is its eigenvalues have to be real. And the reason why is because the eigenvalues correspond to the numerical values associated with the outcome as we wrote here. So if it's a value associated to an outcome of a system, then those values have to be real. As the temperature of a temperature of a room can't be a complex number, or the speed of a car can't be a complex number. So then the eigenvalues associated with those outcomes must be real. Now, let's say we want to measure our observable in our quantum state. So let's say we have a quantum state psi, and we expand it in the basis of energy. So that will look something like this, where it's a linear combination of all the possible energies, energy value, eigenvalues, and eigenvectors. And let's say we want to know the probability of the energy level of E4, which is just a random energy level. Let's draw out of our eigenvectors for this case. So we have two eigenvectors here. And reminder, they're going to be orthonormal to each other. So we have our first an eigenvector here, 1, and eigenvector 2, which has a corresponding eigenvalue as well. So now let's draw our quantum state psi. Just a random drawing of psi. And we can notice that it's very close to this axis over here. So intuitively, we can think that a larger component along the eigenvector here means a larger probability of having that outcome over of this eigenvector. And if you remember back to linear algebra, the way we can find the component along a direction is by taking the linear product of the vector along the unit direction. So the way we do that is taking the linear product. So again, we want to find the energy level E4 on the state side. So we can rewrite that as the following. And once we have this definition, this is coming from here, by the way, we can just move around some terms and have it written as here. Now, we know that all the eigenvectors are orthonormal to each other. So the only non-zero eigenvector in this case will be itself. Sorry. So it'll be itself over here. And then this is just 1. So you're left with the sorry, it has to be the eigenstate corresponding to E4 as well. So then it'll be left as the eigenvalue corresponding to that eigenvector here. So to recap, if psi is an eigenstate, an eigenstate of the observable we were trying to measure, let's say A, then so that A is like follows, then the outcome is going to be the eigenvalue associated with that eigenstate. And the state will be unchanged after the measurement. So the state will be unchanged. Remember that. But let's say the case that psi not an eigenvector of A, then the result will be probabilistic. And this is where the Born rule applies. I won't be deriving the Born rule here, but there is online resources which can walk you through the derivation of Born rule. The Born rule states that for an observable A, which has the eigenvectors of E1 and E2, and the eigenvalues E1 and 2, which are also real, as we stated before, if we measure A in psi, then the outcome will be the eigenvalue with probability of this, where I is 1 and 2. So again, the outcome will be the eigenvalue with the probability of the magnitude squared. So let's do a few examples here. So first, we're going to measure poly z in the off state. As a reminder, poly z can be written as this. The eigenvalues for poly z is +1 and -1, or like here. And the eigenvectors is the off state and the on state. Since we're measuring poly z in the off state, which is an eigenvector, that means the first rule applies, where the eigenstate is where off state is the eigenstate of the observable z. That means that the result will be plus 1 with a probability of 100%, and the state is unchanged. The resulting state will be the off state, as the state is unchanged. But let's take measuring the z in the off state. X in the off state. So poly x can be written as this, and the eigenvalues are plus and -1, corresponding to the eigenvectors of the plus state and the minus state. As you can see, the off state is not one of its eigenstates. So now we have to walk through the math. So let's take the case of the eigenvalue 1. And the eigenvector corresponding to that is the plus state. So then we have to compute the probability, we do the following, where we take the magnitude squared, and we can rewrite this as so, where this is the plus state and this is the off state. Actually, this will be written like this. And if you compute it here, then you get 1/2 times square root of 1, which is just 1/2. So the probability of measuring the eigenvalue 1 will be 1/2. And the state collapses into the state plus 1 like this. I want you to do the same thing but for the eigenvalue of -1 yourself. And that's it. If you have any further questions, feel free to reach out and ask any of us. Thank you.